Swayam Prabha. Digital India. Educated India.
So, that is the next level of minimization algorithm. There are books written on minimization algorithm, constraint optimum and unconstrained optimization, equality constraint, inequality constraint, nonlinear constraint, the whole area of linear programming, the whole area of nonlinear programming, they are all inequality constraint optimization problem. Books written on, there are very well documented algorithms for solving those problems. So, here I am talking about an unconstrained minimization problem of a quadratic function, theoretically asking if finite time convergence is possible. That is the idea. The key idea is not gradient, is conjugate gradient, is called conjugate direction. So, I am going to start by defining a conjugate direction, conjugate vector, and then develop the method of conjugate gradient subsequently. Again, let A be an SPD matrix. Consider a quadratic function which is 1/2 of x transpose A x minus B transpose x plus C. So, with respect to this matrix, I am going to pick a set of vectors, n vectors in Rn. P0, P1, Pn minus 1 are vectors in Rn. Until now, I used to subscript the labels as 1, 2, 3, 4. Here I am starting from 0, 1, 2 and so on, which is similar to what we did in the gradient algorithm, where the initial starting point is x 0. So, I am talking about a sequence x 0, x 1, x 2, x 3. Here we are talking about P 0, P 1, P 2, Pn minus 1. So, in this case I have only a finite set of vectors. So, consider a finite set of n vectors, each of which is a vector in the n dimensional space. Now, I am going to define under what condition these vectors are said to be A conjugate. We have already known that a set of vectors is said to be mutually orthogonal if the inner product of any two distinct vectors is 0, the inner product of a vector with itself is equal to 1. So, that is what is called mutually orthogonal and normal, that is called orthonormal vectors. This notion of conjugacy is an extension of the notion of orthogonality. So, a set of vectors in S is said to be A conjugate if Pi transpose APJ is 0 for I not equal to j, is not equal to 0 when I is equal to j. So, if I assume A is equal to identity, this definition is exactly the definition of orthogonality. If A is identity, it becomes orthogonality, it becomes orthogonal. So, to invent a finite time convergence, a method that can converge in finite time, they introduce this notion of conjugacy, A conjugacy. So, what does this mean physically? I have a vector Pi. If I multiply a vector Pi, I get API. API in general is not equal to Pi unless Pi is an eigenvector. So, I am considering Pi's are general vectors. I have a vector Pj. So, this is the vector Pj. Pj and Pi are not orthogonal, but Pj and APj are orthogonal. And that holds good for every pair of vectors, for every pair of vectors. So, for I not equal to j, Pi transpose APj is 0. If I is equal to j, Pi transpose API is not 0. So, this is the extension of the notion of orthogonality. Now, there is a general concept, I hope you all remember this. Linear independence. A collection of vectors is said to be linearly independent if by picking a set of n constant I can multiply and add them, I cannot create 0. Linear dependence, linear independence, I am sure we have we have already dealt with that. So, a set of vectors can be linearly independent, we just saw the condition. A set of vectors can be orthogonal, I know the set of condition. A set of vectors can be A conjugate, I saw the set of condition. So, what are the implications? Every system of orthogonal vectors must be linearly independent. Every set of P conjugate vectors must also be linearly independent. That is a proof of that. I am going to leave this proof as a homework problem, and if anybody has a difficulty, you can always contact me. I will try to help you, but I would like you to get started with the proof. So, linear independence, orthogonality implies linear independence, A conjugacy implies linear independent. The linear independence of these vectors gives you an idea that I can transfer the basis from one base to another base. Every basis must be linearly independent. So, linear independence of orthonormal vectors is a fundamental property. The proof that A conjugate vectors are linearly independent, that is a homework for you. I would like you to try to use the definition of linear independence. Please do. So, if the conjugate vectors are linearly independent in Rn, please understand I have a set of n conjugate vectors, A conjugate vectors. Conjugacy is always with respect to a SPD matrix. So, if they are linearly independent, they form a basis. If they form a basis of Rn, for Rn I have now two bases. One is a standard basis E1, E2, En. Now, I have a new basis P0, P1, P2, Pn minus 1. So, I am going to change the basis, transformation of basis in a linear space. I have already done how the transformation takes place when I did the module on matrices. So, if P0, P1, Pn minus 1 are linearly independent, if x0 is a fixed vector, for any vector x in Rn, x minus x0 is an arbitrary vector in Rn, I can pick my x0 to be origin, in which case x0 x minus x0 will be x itself. So, by fixing x0 by varying x, I can get quite a variety of vectors. These vectors are vectors in Rn. These vectors have a natural representation in the original basis. Now, I would like to be able to change the representation in the new basis given by the conjugate vector, A conjugate vectors P0, P1, Pn minus 1. So, that means there exist constants alpha naught, alpha 1, alpha n minus 1, such that alpha naught P0, alpha 1 P1, alpha n minus 1 P1 is equal to x minus x naught. Alpha 1, alpha naught, alpha 1, alpha 2 are the coordinates of the same point with respect to the new basis P0, P1, Pn minus 1. So, this is simply a change of basis formula. And we have already introduced the notion of change of basis when we did matrix theory. So, I do not know what alpha naught, alpha 1, alpha n minus 1 are, but I do know it exists, because P0, P1, P2 are all linearly independent and form the basis. So, given this, my aim is to be able to find alpha naught, alpha 1, alpha n minus 1. To do that, what do? I want to exploit the property of A conjugacy. How do I exploit the property of A conjugacy? You multiply both sides by the matrix A. Then you multiply both sides by a vector Pk transpose for some k running from 0 to n minus 1. So, pick a k, multiply both sides by pk transpose A x minus x naught. If I did that, I am going to get, this is a summation over j. Please remember, pk is fixed, j varies. So, this summation now becomes alpha j bk transpose A p j. By the condition of conjugacy, pk transpose A p j is 0 when I is not equal to, when j is not equal to k. It is non-zero only when j is equal to k. Please remember, k is fixed, j is varying. Therefore, every other quantity other than alpha k is 0, and this is equal to alpha k times pk transpose A p k. So, now I can find alpha k. Alpha k is expressed as pk transpose A x minus x k divided by pk transpose A p k. Pk transpose A p k is strictly greater than 0 because A is SPD. So, what does this provide you? This provides you, I have the same vector x minus x naught has two representation, one in the natural basis, another in the new conjugate basis. When I represent to the conjugate basis, I can indeed compute the coefficients of the linear combination based on this formula. So, A conjugacy, by virtue of it being linearly independent, provides a new basis for Rn. So, instead of doing the problem in the original basis, I am now going to do the minimization problem in the new basis. So, it is simply a transformation of the basis for conducting this minimization algorithm. In the case of gradient algorithm, we work to the original space itself, the original representation, the original basis itself. So, using conjugate vectors, now I am going to show I can solve the system A x is equal to b. But before I go there, I want to tell you something. If I have f of x is equal to 1/2 of x transpose A x minus b transpose x plus c, the gradient of f of x is equal to A x minus b, and the gradient of x is equal to 0 means A x is equal to b. So, what does this mean? Every quadratic function leads to the solution of A x is equal to b, and if I have a problem with A x is equal to b, there always exists a minimization problem with A as a matrix where A is SPD. So, that means minimization of quadratic functions and solution of linear system with symmetric positive difference systems are one and the same problem computationally. Therefore, I can think of the conjugate gradient algorithm as one of minimizing a quadratic function or one of solving A x is equal to b. This dual interpretation essentially comes from the tight relation between the quadratic minimization and the solution of linear system. So, let x star be the solution of the linear system A x is equal to b where A is SPD. Let S be a system of A conjugate vectors. X naught is the initial guess starting point. So, A times A x naught x star minus x naught, x star is A inverse b, we already know that, right. So, A times, so x star is equal to A inverse b. So, if I substitute it in here, this becomes b minus A x naught, that is equal to R x naught. So, A x naught minus A times x naught minus x star minus x naught is R naught, that is the initial residual. Now, any vector, please understand what is that we have shown, x minus x naught can be expressed as alpha j times p j, j is equal to 0 to n minus 1. That is the result that we showed in the previous slide. Any vector can be expressed with a linear combination of conjugate vectors. Therefore, x star, the minimizer, is any vector, I do not know what it is, but this minimizer can be expressed as x minus x naught is equal to summation alpha j p j. So, if I kick the x naught to the other side, the minimizer has a representation like this, and I have shown in the previous slide alpha j can be recovered, alpha k can be recovered by this, and this is simply p k transpose A R naught divided by p k transpose A p k. So, alpha k can be represented like this. So, if I can find alpha k, I already know p k. starting with any solution, starting with any initial point, I can express a solution as a linear combination of the conjugate directions. That is the idea here. In other words, I can express the unknown minimizer as a linear combination of the n conjugate vectors. This ability to express the unknown solution as a linear combination of the A conjugate vectors with a known coefficient. So, what is that I am assuming? I am given, so if you are given a set of A conjugate direction, then I can compute the minimizer as a linear combination of the conjugate direction using no more than n vectors. And we have already seen solving A x is equal to B is the same as minimizing 1/2 of x transpose A x minus B transpose x plus C. Therefore, using the notion of conjugacy, I am able to express the unknown minimizer as a linear combination of conjugate vectors. Please understand, this we did not do in the gradient method. So, this brings out the power of the conjugate direction. Once this was realized in the late 40s, mathematician could extend this to in the form of an algorithm. That algorithm is called conjugate gradient method. So, conjugate direction framework and the conjugate gradient method. A framework always gives rise to an algorithm. So, the notion of A conjugacy and its power is what I am talking about. So, having established the power of conjugacy, A conjugacy, now I am going to go back to my quadratic minimization problem. Please understand how we got here. We are a good algorithm in gradient method, but we soon realized it can be very slow. It works very well more often than not, but there are exist problems where it can be very slow. We did not want the slow behavior. We want for all instances of the problem the behavior to be better. So, we sought a finite time convergence. That means I needed a newer framework. The newer framework is provided by the concept of the existence of A conjugacy direction. Thus far, we talked about the properties of A conjugate direction. Now, given a set of A conjugate direction, I am now going to talk about quadratic minimization problem. I am going to develop a framework for the algorithm. So, f of x is equal to 1/2 of x transpose A x minus B transpose x plus C. The minimizer is given by the solution of A x is equal to B. The residual is B minus A f x, B minus A f x. I want to be able to minimize f of x is equal to R x transpose R x, which is B minus A x transpose B minus A x, and which is equal to exactly the solution of this problem, in which case C is equal to 1/2 of B transpose B. So, I am trying to express this function in terms of the residual, that is all. So, these two problems are intimately associated with each other. The gradient of this is given by A transpose x is equal to A transpose B. Therefore, if I want to rewrite this as A transpose A x is equal to A transpose B, but A is non-singular. So, if I multiply both sides by A minus transpose A transpose A x is equal to A minus transpose A transpose B, this is equal to identity, this is equal to identity, that implies A x is equal to B. This is equal to A is equal to B. So, you can look at this from various ways. I can define a residual and consider a corresponding f of x, or you can start with a general f of x is equal to 1/2 of x transpose A x minus B transpose x plus C. The A and A are the same, the B's are the same. So, these are two different ways of looking at the same problem. These two problems have solution given by A x is equal to B, where A is an SPD matrix. You remember what the idea? The idea is to be able to replace the original coordinate into the new coordinate system given by the conjugate basis. So, I have been given n conjugate vectors, each of them are n vectors. I am now going to define a n by n matrix, I am going to call it capital P. So, what is capital P? Capital P is a n by n matrix whose columns are the A conjugate vectors P 0, P 1, P 2, P n minus 1. Now, I am going to change the matrix P transpose A P. You remember, if I have a matrix A, B inverse A B and B transpose A B, there are two types of transformation. This is called similarity transformation. This is called conjugate transformation. Conjugate transformation, similarity transformation. So, if I choose B is equal to P, I get this. So, you can think of this as a conjugate transformation of the matrix P, I am sorry, the matrix A. And what is P? P is the matrix of orthogonal, I am sorry, A conjugate direction, given A conjugate direction. So, P is given by this, here is A, P transpose is a column. So, P is a row, this is the column partition, this is the row partition. I can express this as a matrix. If I express this as a matrix, what is this matrix going to be looking like? This is P 0 transpose A P 0, P 0 transpose A P 1, all the way up to P 0 transpose A P n minus 1. By conjugate direction definition, this is 0, this is 0. What is the next one? P 1 transpose A P 0, P 1 transpose A P 1. This is P 1 transpose A P n minus 1. By the conjugate direction property, this is 0, everybody else is 0. So, this is the diagonal matrix. So, this is D 1, D 0, D 1, D 2, D n minus 1. So, if I define the diagonal matrix to be P I transpose A P I, this now becomes a diagonal matrix, which I am going to call it D. Look at that, the beauty of this. The matrix A has a original representation, the original basis. The matrix A, when transformed into a new basis, it becomes a matrix which is given by the conjugate transformation. The conjugate transformation is P transpose A P. So, conjugacy applies both to the matrix transformation as well as to the method, conjugate method. So, A given of all the matrices, diagonal matrix is the one that is the simplest structure. So, what does this say? The matrix A has a original dense structure, now assumes a diagonal structure in the new basis. Diagonal matrices are very easy to handle. This is the reason we want to be able to transfer the matrix A from the standard basis to the conjugate basis. Now, let X be the ultimate solution, or x 0 initial point P alpha. So, let x is equal to x 0 plus P alpha. So, any point x in the original space can be represented by x 0 plus P alpha. So, alpha is a n vector, Now, I am going to decompose f of x. I am going to decompose the representation of f of x using this. Now, please understand, x minus x 0 is equal to P alpha. X minus x 0 is the original point, it represents the same point by P alpha. So, alpha are the new coordinate system in the basis P. So, that is the relation between x minus x 0 and P alpha. So, R 0 is B minus A x 0, we already know. D is equal to P transpose A P from the previous slide, D is equal to A P transpose A P. So, f of x, where x is equal to x 0 plus P alpha, and I already know the functional form of f of x. What is that? 1/2 of x transpose A x minus B transpose x plus C. So, if I substitute x is equal to x 0 plus P alpha and simplify, you go from here to here to here to here. So, there is a good amount of simplification needed. So, I am substituting x by x 0 plus P alpha. x by x naught plus p alpha, x by x naught plus p alpha. You open the brackets, you distribute, you recompute everything, you get this term minus this plus this term minus this term. This term is a constant and this term is simply f of x naught, that is a constant, because x naught is a constant, f of x naught is a constant. This term is a quadratic function, this is the linear function. We just showed P transpose AP is diagonal. So, this is simply k is equal to 0 to n minus 1 dk alpha k square, and this is R naught. So, R naught transpose P alpha, this is capital P, P alpha, this is the matrix capital P. Therefore, this is equal to R naught transpose P k alpha k, k running from 0 to n minus 1. I can rewrite this as summation f of x k. I am going to define a new function g k of alpha. So, there is alpha k square dk, this is R naught transpose p k alpha k. So, I can define g k alpha k as a function of 1/2 of dk alpha k square minus R naught transpose p k alpha k. Therefore, by combining this using this definition, my g of alpha is given by this. So, what is this now? F of x is the original function in the original basis, g of alpha represents the same function in the conjugate basis. Look at this now, how I am transforming things now. Originally, I am given a original space, I concocted a new space called the conjugate basis space. I am assuming somebody gave me the conjugate direction. I still have not told you how to find the conjugate direction, which we will do very shortly. The points have the same point have two representation in both the bases. The function also has two representation in the two bases. The representation of point induces the representation of functions. So, g of alpha is represent the same function as f of x. And what is the advantage? The advantage is divide and conquer. Alpha is a scalar variable. Alpha is a scalar variable. So, g of alpha is a one dimensional function. So, I am trying to represent an n dimensional function as a constant plus a sum of n one dimensional function. A divide and conquer is active here. Divide and conquer, active here. Please understand, in the case of gradient method, we divided the n dimensional minimization problem into a sequence of one dimensional minimization problem. Here, I am representing an n dimensional function as a sum of n independent one dimensional function, each one along the linearly independent direction given by the conjugate vectors. It is this ability to break down a more complicated function into a simpler form by transforming the basis from the standard basis to the conjugate basis underlies the success of this method. That is the mathematical transformation that made this method to be very popular and guarantee finite time convergence. So, divide and conquer principle of action. So, minimizing f of x is equal to minimizing x naught plus alpha p. No, I should have said this is, I am sorry, this is minimizing p alpha, sorry, minimizing p alpha, p is a matrix. And from the previous case, this function is called g of alpha. So, g of alpha at the end of the slide we have already shown is the sum of, I am sorry, is the sum of all these. So, I am going to substitute this in here. G of alpha is represented by the sum. I am going to minimize this over alpha. So, the minimizing the sum is the sum of the minimums, because x naught is a constant. Please understand, I am minimizing the sum is equal to the sum of the minimums. Why? The alpha k are in different directions, they are independent directions, so one does not affect. So, G1 depends on alpha 1, G2 depends on alpha 2, G3 depends on alpha 3. So, to minimize G1, G1, G2, G3, I can simply do the sum along each of these directions. Therefore, I have converted the problem into a minimization of n one-dimensional functions. Please understand, gk alpha k depends only on alpha k. So, it is this independence that I bring to the structure of the function by changing over from the standard basis to conjugate basis is the secret of this approach. It is the secret sauce that this approach uses. Now, we also know this G, what is the form of this G? This star, you may recall this G is the same G that occurred in gradient method. It is a quadratic function of a single variable. So, this G, now I am going to compute the minimum with respect to alpha k. This is a quadratic function, second degree, first degree term, scalar valued function of a scalar. So, G is R to R, is a very basic univariate calculus, undergraduate work. So, the gradient is 0 is equal to given by this equation. So, alpha k is given by this ratio, which is equal to p k transpose b minus a x naught by p k transpose a p k. P k transpose a p k. This should be written as p subscript k. This is the same formula we derived earlier, but we are trying to do in the context of minimization. So, this brings us a framework. Wow, this is what we want to achieve. So, if you give me a conjugate function and given an arbitrary point, I can define the initial residual. I am assuming I am given, somebody gave me a set of n a conjugate direction. I can now express my minimization algorithm as a finite loop. Wow, this is the achievement. In the case of gradient algorithm, I wrote for k is equal to 0, comma 1, comma 2, comma dot 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 dot, I had an exit condition. Here is a finite time do loop. In a finite time do loop, you do not need an exit condition. In fact, we are going to introduce an exit condition because we may be able to shorten the number of iterations needed. So, how does the algorithm framework looks like? Given p naught, p1, p2, pn, given the starting point x naught, I can compute alpha k for k is equal to 0. Then I can compute x1, I can compute r1. If r1 is 0, I am already at the minimum. You are done in one iteration, but it may not happen. If it is not 0, then continue step alpha 2, you continue this way and you do no more than n minus 1 iterations. So, this framework essentially provides the mathematical wherewithal for us to be able to feel that finite time convergence is indeed achievable. And this was done late 40s, early 50s, 51. Please understand, the computers came into existence around that time. So, the potential for implementing the iterative algorithm became very popular. So, mathematicians are looking for development of iterative algorithms starting from Kantrovich for minimization algorithm. So, the time was very ripe and people are working on various aspects of algorithms, essentially concentrating on iterative algorithms. So, given xk and pk, I consider the 1D minimization problem. I substitute in the function for f of x, I simplify this expression, I get this. If I find the minimizer, this is equal to that, and that is essentially verify the expression for alpha k in step 1. See, this is the algorithm. I verified the algorithm in step 1. Verify the expression in step 3. So, the xk plus 1 is going to be equal to alpha k x p k, this is at step k, alpha k p k. So, r k minus 1 is equal to b minus a x k plus 1, x k plus 1 is given by this, you substitute this for x k and you get an expression this is equal to r naught, this is equal to r naught, this is equal to alpha j a p j alpha j a p j. By the iterative process, this is simply alpha k a p k. By the iterative process, this is simply alpha k a p k. Therefore, r k plus 1 is equal to r k minus alpha k a p k. That is the expression for the r k plus 1. So, I am verifying and I am trying to check, recheck everything the way we have designed it. Now, relation between r k and p k. You please remember, in the case of a gradient method, there is no p k, there is only r k. We showed that r k plus 1 is perpendicular to r k. Here, r k gives you the direction of the negative of the gradient, p k gives you the conjugate direction. So, we want to be able to understand what is the relation between r k and p k. R k and p k relation can be examined by p k transpose r k plus 1. R k plus 1 from the algorithm is r k minus alpha k a p k. Now, by substituting the value of alpha k from step 1, we can see this is 0, and we already know r k plus 1 is b minus a x k plus 1, that is the negative of the gradient, negative of the gradient, negative of the gradient. Therefore, from this we can conclude that x k plus 1 minimizes f of x k along the line x k plus alpha p k. So, that is an important property. So, here is x k, here is the line p k. I am going to pick a point x k plus 1, which is equal to x k plus alpha k p k. And how is this point decided? This minimizes the function f of x along the line x k plus alpha p k. That is the one dimensional minimization that we did in the case of a conjugate, in the case of gradient method. What is the only difference? In the case of gradient method, p k was r k, there is no p k in there, there is only r k. Here there is an r k, there is a p k, there is an r k, there is a p k. Please understand, I do not use r k to be able to search. So, I am updating using p k, yet I am computing r k. R k I am computing because my alpha k depends on r k. So, I use r k differently than I used in gradient algorithm. In the gradient algorithm, I minimized the function along r k. Now, I am minimizing along p k. So, that is the only difference, that is the primary difference. That is the primary difference. So, this essentially tells you the basic idea of the gradient algorithm is kept up here. That means, I am a given point, I have such direction, I am trying to find the next base point to be the point at which the function attains the minimum value along that direction. Now, it is a homework for you. I would like you to be able to verify p k transpose r k plus 1 is equal to p k transpose r k plus 2, p k transpose r n, they are all 0. That means, they are consecutively orthogonal to each other. Also, p k transpose r k, p k transpose r k minus 1, p n transpose, I am sorry, p k transpose, this must be p k transpose r naught, they are all equal. These are all very good properties of this algorithm. I would like you to be able to, compute this and verify. Now, I am going to talk about an important property of the conjugate gradient algorithm, is called expanding subspace property. What is expanding subspace property? So, I start at x naught, I have a direction p naught, I come to x 1, I am going to do a direction p 1, p 1 is only a conjugate to p naught, then I am going to find x 2. Please understand, x 1 is minimum only along the direction p naught, x 2 happens to be the minimum along the direction p 1 along at the point x 1, but it turns out x 2 is also the minimum of the function in the 2 dimensional subspace spanned by p naught and p 1. That is what is called the expanding subspace property. Expanding subspace property. That means, so to do that, let us look at x k plus 1. X k plus 1 is equal to x naught plus alpha naught p naught, alpha 1 p 1, alpha n p n. minus 1, there is no Pn. So, please understand this is n minus 1, n minus 1. Rk is equal to b minus ax k plus 1. If I multiply both sides by a and subtract from here, and this is equal to r naught minus alpha naught ap naught, alpha 1 ap 1 and so on. These are linear combinations. These are linear combinations of vectors. So, if I took the inner product of with respect to Pj, Pj transpose Rk plus 1 is equal to Pj transpose R naught minus alpha j times Pj transpose Ap naught. I have a I can substitute for Rj from step 1 and you can verify this is 0. So, what does this mean? This means Rk plus 1 is perpendicular to the span of k minus 1. So, the gradient, the negative gradient is perpendicular to the span. If it is perpendicular to P naught P1 Pn minus 1 means what? It is perpendicular to the span of that. That means the span of this is a subspace. Therefore, the successive residuals are orthogonal to ever increasing subspaces, first dimension 1, then dimension 2, then dimension 3, then dimension k, then dimension n. Once I come to the dimension n, there is no more place to go, I have converged to the optimum point. So, that is what is called expanding subspace property. That means xk plus 1 minimizes f of xk over the subspace spanned by, that is what I finished talking about, I am trying to quantify that, x naught plus span of that. So, xk plus 1, in addition to minimizing f of x along the direction xk plus alpha pk, it also minimizes along all the previous direction together. That is idea. This must be k, sorry, k. So, if I apply this to all, xn minimizes f of x, this must be xn, xn minimizes f of x and Rn, xn minimizes f of x and Rn. Therefore, so what is that we have done? We are trying to talk about the properties of the conjugate direction framework. There are two directions, residual and the conjugate direction. Residuals are used to compute the step length parameter. The conjugate directions are used to search for the minimum along the conjugate directions. So, it is a combination of using both conjugate direction that is given to you and the residual that you compute along the way. Please understand the algorithm from the algorithm. P's are given to you, you compute the residual directions. So, when you do that, what is the relation between P and R is what is explored in here. So, xn minimizes f of x and Rn. So, what is the finite time convergence theory? If f of x is equal to 1/2 of x transpose ax minus b transpose x, please remember I am not adding a constant. Adding a constant means I am pushing the function up or down, it does not change the minimizer. So, if you are given the function and if you are given a set of A conjugate direction, the conjugate direction framework guarantees convergence in at most n steps, What is the implicit assumption? The implicit assumption is the computations are error free. Why computations are error free? Please remember that. If I say two vectors are orthogonal, A transpose B must be equal to 0, which is equal to summation ai bi, I is equal to 1 to n. If I compute the product of ai bi and add them up, will I ever get 0? Very seldom, very rarely. You will not get 0 in finite precision arithmetic, because multiplication of ai bi cannot be done perfectly, addition cannot be done perfectly. So, the mathematical concept of pure orthogonality can be realized only approximately in computers. Likewise, the mathematical concept of A being A and B being A conjugate being 0, when A not equal to B, it also can be checked to approximately. So, what does it say? I do not know how you guys design computers, but if you can give me a perfect machine is one that computes addition, multiplication, subtraction, addition without any errors, then my framework will essentially give you the exact minimum in no more than n steps. Why no more than n steps? Please look back at the algorithm. If Rk is 0, then x star is equal to xk plus 1, I get out. That is the exit condition. Even though it is a finite loop, I have included exit condition, but in some problem it can happen. That depends on the structure of the eigenvalues of A. Structure of the eigenvalues of A. So, what is that we have in principle? If you have a quadratic function with a symmetric positive definite matrix, and if you are given a set of A conjugate direction, and if your computer is error free, so there are lots of if. I am given a model problem with symmetric positive definite matrix. I am given a set of A conjugate direction, and I am assuming the presence of an error free computer, perfect computer that has no round off errors. This framework will provide you a finite time algorithm to be able to compute the minimum. Computers, mathematicians, they do not design, that is for somebody else to design. So, we have to wait and use whatever they give us. So, mathematicians have no control over that. So, I will use the machine whatever you give me. Function to be minimized, you give me the function to be minimized. So, what is the next thing? I want a set of A conjugate direction. So, the whole analysis rests on the assumption that I have access to a set of n A conjugate direction for a given A. Now, please understand, if it depends on the problem. The A conjugate direction depends on the value of A, which is 1/2 of x transpose A x minus B transpose x. So, every problem has an A, and every A has an associated set of A conjugate vectors. Now, I assumed so far, given a matrix A symmetric positive definite, there exists A conjugate direction. I have not shown that A conjugate direction exists. I have not shown how to go about finding A conjugate direction. If I address this question and combine it with the conjugate direction framework, I get an algorithm called conjugate gradient method. So, conjugate gradient method is a practical way of implementing conjugate direction framework, where I am going to have to compute the conjugate direction along with the iterative process. Nobody gives you anything, you have to create everything yourself. So, this process of automatically creating the conjugate direction along the iterative process is the new thing I am going to have to add to the algorithm to make it a workable algorithm where there is no assumption made. So, before we do that, I want to show that conjugate direction exists and how to find at least one set of conjugate direction. So, this is a mathematical question. Given a SPD matrix, how do you find a conjugate set, a set of conjugate direction? Given A is SPD, you remember we have an eigen decomposition, spectral decomposition. If A is SVD, A Vi is equal to Vi lambda I. If V is equal to V1, V2, Vn and lambda is equal to lambda 1, lambda 2, lambda n, this set of n relation can be succinctly related said as AV is equal to V lambda. So, VV transpose V transpose is I, they are orthogonal. So, what is that I have? AV is equal to V lambda. If I multiply both sides by V transpose, AV V transpose is equal to V lambda V transpose, that implies A is equal to V lambda V transpose, because we already know V transpose V is identity. So, this is called the eigen decomposition. This is called the eigen decomposition. Another way of looking at it is you multiply both sides on the left V transpose. So, from here V transpose A V is equal to lambda. Is equal to lambda. So, how does this look like? This looks like P transpose A P is equal to the diagonal matrix, you remember? So, if P is the A conjugate direction, we have already shown P transpose A P is diagonal. So, these two relations are exactly one and the same, except that P is replaced by V and D is replaced by lambda. So, what does this tell you? Given a matrix A, the eigenvectors are A conjugate. Wow! The eigenvectors are A conjugate. That means conjugate direction exists. What is an example of a conjugate direction for a given symmetric positive matrix is the set of all eigenvectors of A constitutes the A conjugate direction. Therefore, I can implement the conjugate direction framework using eigenvectors, but there is a catch. Computing the eigenvectors of a given matrix is very demanding. If I have a larger matrix, computing the eigenvectors of a given symmetric positive matrix, the complete system, I want all the eigenvalues and all the eigenvectors, that is computationally demanding. Please understand, computing computing the conjugate vectors, computing the conjugate vectors is only a part of the problem. If I am going to spend too much time in computing the solution for the part of the problem, the whole methodology becomes too expensive. So, while in principle I can use this idea, in practice this is to be avoided. So, we answered one question, but another question popped up. What is the first question we answered? For a given matrix A, the eigendirections are A conjugate direction. So, A conjugate directions exist, eigendirections are one example. While it exists, I cannot use them because they are computationally very demanding. Therefore, what do I need to do? I need to be able to add a class of method by which I can generate the A conjugate direction, and that gives rise to what is called the conjugate gradient method. I want you to understand conjugate gradient method, books have been written on this algorithm. So, I am now going to describe the conjugate gradient method. So, what is that I have argued so far before I get into the algorithm? I was driven by the need for a finite time convergence. I concocted the concept of A conjugate direction. If I am given a set of A conjugate direction, I proved theoretically that I could have an algorithm using which I can have n step convergence that exploits the linear independence of the conjugate direction conjugate vectors. The linear independence of the conjugate vectors is the key. Once I have a linearly independent vectors, I can transform the basis from the standard basis to the A conjugate vectors and the magic happens. Then we ask the question, who is going to give you the conjugate direction? Nobody is going to do, you have to derive yourself. So, we said that an example of A conjugate direction is given by eigenvectors, but computing the eigenvectors is very expensive. Now, I am going to describe a conjugate gradient method, which is an algorithm that embeds the idea of conjugate direction and the method of generating conjugate directions. So, I have a new algorithm. This is 6 steps. This is called the conjugate gradient algorithm as opposed to simply gradient algorithm. X naught is the initial point, R naught is equal to B minus A x naught. So, you remember I need to pick up the residual is given by the initial condition, automatic. I do not know what P naught is. So, I need to pick a set of n conjugate directions. So, without loss of generality, I am going to pick the first direction to be equal to R naught, the first direction to be equal to R naught. Here I am going to give you an analogy. In the QR decomposition, I am given a set of n linearly independent vectors. I want to create a set of n orthonormal vectors. So, what did I pick Q1 to be? Q1 to be H1, the first vector itself. The same thing in here. R naught is the first the residual. So, without loss of generality, the first direction I can pick arbitrarily, I am going to pick P naught is equal to R naught. So, if P naught is equal to R naught, I have an iterative process from k is equal to 0 to n minus 1. Step 1 is the same as the previous case, step 2 is the same, step 3 is the same, step 4 is a test for convergence. So, in step 1 I compute alpha k. Please understand, alpha k can be computed by two distinct formulas. I want you to know there are books written on simply conjugate gradient algorithm. I am not going to prove every little part of it. Proving the details of this will take probably 3-4 lectures. There are beautiful books written. So, I am going to leave this part of the proof to those who want to master these techniques to very good textbooks, but I am going to give you the guts of the algorithm, the pseudo code if you wish. Alpha k can be used by two formulas. You can use any one of them in your computation. Then I am going to update the iterate. Iterates are updated by searching along the conjugate direction. Now I compute the new iterate. If the inner product of the iterate with itself, the residual with itself, means the square of the norm of that, if it is less than epsilon, exit. So, it is a finite loop with an exit condition. That means there is a potential for me to converge even earlier. The last two steps, these are essentially the same as the old one, conjugate direction. The last two steps are the one that is going to generate the conjugate direction. So, Pk plus 1 is equal to Rk plus 1 plus beta k Pk. Look at this now. The new conjugate direction at time k plus 1 is equal to the linear combination of the old conjugate direction Pk plus the residual vector. The residual vector, please remember, is the direction of the negative of the gradient. So, I am using the negative of the gradient and the previous conjugate direction to be able to define the new conjugate direction. So, there is a linear combination of two directions. So, the gradient is involved, conjugate gradient, conjugate direction is involved, that is why it is called conjugate gradient method. It uses gradient vector, it also generates a set of conjugate directions. And in here beta k is the coefficient of linear combination. The coefficient of linear combination beta k can be again calculated by two formulas. Just like alpha k is given by two formulas, beta k is given by this formula. So, what is that you do? K is equal to 0, x naught is given, r naught is known, compute alpha naught, compute x1, compute r1, test for convergence. Then you compute beta 1. So, I already beta 1 is a constant, and you compute P1. You already know P naught, you are going to compute P1, repeat the process, repeat the process, repeat the process in no more than n steps. The algorithm will converge, and there is a potential to exist from here in infinite time. So, what is the essence of the story? You now, this is conjugate direction, not direction. You are generating the conjugate direction by a simple method. If you look at mathematically, these two steps are very similar to these two steps in terms of computations. Every one of these steps involves what? There is a vector, sorry. Every one of these involves what? There is a vector, you update the vector. There is a vector, you update the vector. There is a vector, you update the vector. So, you update the iterate, you update the residual, you update the conjugate direction. So, step 2, step 3, step 6 are 3 updates of the iterate, the residual, and the conjugate direction. These updates requires the coefficients for the linear combination alpha k and beta k. So, 3 updates, 2 parameters, 3 plus 2 is 5, 1 test condition, 6 steps you get out. So, this pseudo code is very easily implementable. So, what is the homework problem for you? You take x transpose Ax. You remember I have given you lots of good exercises to compute x transpose Ax. I would like you to be able to solve that numerically by gradient algorithm and the conjugate gradient algorithm. Gradient algorithm and the conjugate gradient algorithm. So, some of the properties, the conjugate directions are computed internally in steps 5 and 6. It permits alternate choices of alpha k, beta k. PKs are A conjugate, so generated. So, there is a proof. I am not going to get involved in that because I can spend 5 more lectures on conjugate gradient itself. As in gradient algorithm, Rk plus 1 is perpendicular to Rk, but Rk is also perpendicular to the span of Pk minus 1, sorry, Pk minus 1. This is Pk minus 1. No, let me write that clearly. So, this becomes Pk minus 1. At the kth step, the negative of the gradient is orthogonal to the span of P 0 P 1 Pn minus 1. We have already seen that is the expanding subspace property. It is this expanding subspace property gives you the desired behavior. There are a few other properties I would like you to be able to verify. The span of P 0 P 1 P 2 Pn minus 1, that the whole space is also equal to the span of R 0 R 1 Rn minus 1. It is the same as the span of A R 0 R 0 A R 0 A square R 0 A to the power of k minus 1 R 0. This span in mathematics is called Krylov subspace. This is capital K. Krylov is another Russian mathematician. Krylov subspace of dimension k generated by A and R 0. So, R 0 is a vector, A is a matrix. I am going to generate a set of vectors R 0, A R 0, A square R 0, A to the power of k minus 1 R 0. So, a set of k vectors that are given in here. These k vectors are linearly independent, they generate a subspace. That subspace is called Krylov subspace of dimension k generated by A and R 0, and generally denoted by Krylov space of dimension k generated by A and R 0. The theory of Krylov subspace is very fundamental to the further analysis of the conjugate direction method. I am not going to go into that part of the theory. This theory is very well understood, is very well documented. In our book, we have described we have given the proofs of every one of the results that is needed here. So, I am going to give the reference to my book for further details. Now, in practice, so theoretically conjugate gradient method is a winner, but if I put it in a real computer, just as we saw earlier, orthogonal vectors, the inner product must be 0, in practice it will not be 0. So, A conjugacy, orthogonality we cannot verify precisely. So, what does the theorem say? The theorem says in no more than n steps I will converge to the minimum. So, in a real machine, if you start at x 0, if this is x star, in n steps you will come into a small neighborhood around x 0, x star. You will not be on the top of x star as we would like it to be, because of we have lost few things because of conjugacy cannot be computed exactly. So, there is going to be an error. So, the question here is that how do I improve my accuracy? One way to improve your accuracy is start at x 0, go up to n steps to get an x star, then you set x 0 is equal to x star, you do a new x double star, then you x 0 is equal to x double star, you go to x triple star. So, what is it I am trying to do? From x 0 I went closer to it, then therefrom I am going to still going to be closer to that, So, it has been found in practice, if you iterate these steps no more than 3 times, in no more than 3n times, I should be able to get very good accurate result. So, what does this tell you? Theoretically, it is a direct method. Theoretically, I should be able to do anything in no more than n steps. Practically, it is not a problem of the algorithm, but a problem of the computer, because we still do not know how to make computers with infinite precision. The method suffers because of the round of errors. The round of errors try to make it iterative in nature. Therefore, how do you compute the ratio of the errors due to this iterative techniques? You remember the same error xk minus x star that we used in the gradient algorithm. You remember the same square of the norm of the energy norm of the error, E of xk divided by x 0 is less than or equal to square root of kappa 2 minus 1 divided by square root of kappa 2 plus 1 to the power k. And you already know lambda 1 by lambda n is spectral condition number. This number is less than 1. This number is much smaller than the number that we got in the case of gradient method. So, this converges as k increases very faster. So, even though in practice it looks like an iterative algorithm, the convergence is much faster than the gradient algorithm. There is no zigzag behavior here. So, I can also compute the number of steps needed by setting epsilon is equal to 10 to the power of minus d. So, this is the expression. I want this to be equal, this will be less than 10 to the power of minus d. So, if I took the logarithm of this equation, I get this relation. Therefrom, I can say k star is equal to d plus 1 square root of kappa 2 by 2. This relation can be very easily established. That is a homework problem for you to verify. So, in practice it works as a iterative algorithm where I can compute the number of iterations needed for the accuracy to be of the order of 10 to the power of minus d. Means what? In here I want to be able to come to a point which differs from the actual minimum only at the 6th decimal. In some problem I may require 2 decimals, in some problem I require 5 decimals, in some problem I require 15 decimals. The accuracy depends on what you want. So, the number of iterations needed depends on the degree of accuracy and the condition number kappa. It is independent of n, the dimension of the problem. So, I am now going to compare a comparison. Epsilon is 10 to the power of minus 7. For a gradient method, 10 to the power of 4 requires 40,000. Here is only requires 730. So, this comparison tells you conjugate gradient method beats the gradient method hands down. Now, I am going to go over some exercises. Verify the relation for E of x k with beta k is equal to this. Prove Cantor-Gini inequality in site 16, that you have to go to the Wikipedia. That is a nice proof. Implement the gradient algorithm and the conjugate gradient algorithm in MATLAB. Yes, MATLAB has a version, but I do not want you to use the MATLAB. I want you to code and I want you to compare your algorithm with the MATLAB algorithm. Now, I am going to give you a new problem. A is equal to 1 0 0 2 is a symmetric matrix, x is x 1 x 2, f of x is equal to 1/2 of x transpose a x. Apply the gradient algorithm and verify that the x of k can be denoted by this when x naught is 2 1. When x naught, see, this is a very beautiful idea that you are going to compute the iterates in closed form. So, the iterate at step k is given by this. Using this, show that the value of the function from k to k minus 1, k to k plus 1 decreases by a factor of 1 over 9. That means, f of 1 is 1 over 9 times f of 0. If f of 2 is 1 over 9 times f of 1, which is 1 over 81 times f of naught. Draw the contours of f of x and superimpose the trajectory. That means, you have to draw the conjugate and then superimpose the trajectory x k along that to visually demonstrate the convergence. That means, show that starting point, the contours and how the function approaches the minimum in the case of a gradient algorithm, and also redo it in the case of a conjugate gradient algorithm to graphically display. Now, where do you going to get matrices? Consider the 4 by 4 grid. You remember the example for the least square problem. I have discussed this in great detail. Distribute 2 observations in each of the grid boxes, a total of m is equal to 18 observation. So, I have n is equal to 6, m is equal to 18. Build an interpolation matrix which is 18 by 16 which I have already talked about. Generate 18 vectors of observation, add noise is given by the Gaussian noise sigma square is the variance, which is the parameter. Construct z minus hf transpose z minus hfx. That means I am trying to give you a practical problem using which you can build your objective function. Here you build the matrix H yourself, nobody gives you. So, this is the objective function to be minimized. Apply the gradient algorithm, conjugate gradient algorithm to minimize this f of x, and plot f of x k versus k for each and comment on your result. So, what is that? This is k, this is f of x k, this will be the trajectory of gradient method, this will be the trajectory for the conjugate gradient method. The conjugate gradient method converges faster than the gradient method. So, this algorithm should help you to see whether the curve for convergence for the conjugate gradient algorithm is well below that of the gradient algorithm. So, this is a very good class project. Unless you do these kinds of class project, you cannot say I understand the behavior of this algorithm very well. So, with that we come to the end of the module on minimization. So, now I am going to give some closing remarks. We started with the modeling least squares problems, we introduced the notion of optimization. We introduced the notion of optimization and we solved the optimization problem in one of two ways, either solving linear equation Ax is equal to b that led to the whole host of matrix decomposition algorithm. The other way would be to directly minimize it using sequential minimization technique, where I compute the gradient, do not equate to 0 and follow the gradient. That led to gradient algorithm, that led to conjugate gradient algorithm. So, with this class of modules, we have talked about modeling and estimation of parameters of the model using good optimization techniques, either using the matrix based algorithm or sequential minimization algorithm. So, that is a big chunk of lectures relating to data modeling. Thank you. We will continue next class.